Yo, what's up, guys? Welcome back. Uh, well, yeah, welcome back. Episode, man, 87 or something. Let's check it out. Let's check out our Pokemon sound of the day. I think it's 88 today, actually. We have a Grimmer today. Let's listen to the sound. Jeez, what is that? I don't even... Blah, blah, Grimmer. Blah, blah, Grimmer. Okay, last one. Blah, blah, Grimmer. Hang on, I want to check when the NCAA March Madness Championship is tonight. Chip game time. 7:50. Ooh. Sure, that'll work. Alright, let's take a look at some problems today. Let's go to our... Let's go to our link list section. To go to LinkedIn, and we have to go to this guy's profile. I believe it's this one. No, it's not this one. Bro, where's this guy's stuff? Load balancing algorithms, dude. What is this garbage, bro? Cracking the Google interview. It's definitely not this one, bro. Like, no shot. God damn it, dude. Alright. I guess we're just gonna go straight back to... Okay, let's just, I don't know, let's just search some graph problems or something. Start off with the typical graph problems. I will search by acceptance. Man, my eyes, dude. Oh my gosh. Okay. Let's do the most widely accepted problem. All paths from source to target. Just to like warm up a little bit. Given a erected acyclic DAG of n nodes labeled from 0 to n-1, find all possible paths from 0 to n-1 and return them in any order. Okay. So I believe this is DFS straight away. I mean, I guess we could use BFS too. Given a acyclic graph DAG. Zero 1 3 0 2 3. Okay, acyclic means no cycles, right? I think. Okay. So, since we can use both here, I'm going to use DFS, right? Because that was the most intuitive to me. I saw this problem, in an interview. I probably do DFS here, right? I know this is probably a little bit overkill for this problem. But I'm going to convert. I always start by converting this to an adjacency list for me because it's easy to kind of think about an adjacency list. I know you probably don't have to. Just print the graph actually. I guess technically it is an adjacency list because this is node 0. This is node 1, node 2, node 3. So technically I guess it is in a way. But we're going to convert it anyway to a hash map, right? DJ list, we pass in our graph, right? We loop through, we create our graph in here, right? We do for I in the graph. We want to check first. Well, AB is equal to I. 1 to 2. No. Well, AB wouldn't be I because this isn't A. This is AB and AB is an edge. So I guess like it would be for I in enumerate graph. Enumerate graph. Well, if I not in graph, we would do, well, graph I is equal to this, right? Then we would need to do, well, AB is equal to edge, right? Zero, 1, 0, 2. And then we need to do, well, graph of I append A graph I dot append B. And let's call it here so we can call our graph is equal to ADJ list, and we pass in our graph. Oh no, we'd probably want to call this ADJ list. It's equal to ADJ list graph, and then we just print our ADJ list. Okay, we got no output. Why do we have no output? passed in our graph. Okay, we redefined it here, so we need to call this ADJ list. We got ADJ list. ADJ list, append, and then we want to return our ADJ list. We never returned anything. Oh, we want to put this outside. Okay, I think we have to do for I and AB like this. Enumerate, get rid of this. Not enough values to unpack. I'm not sure what's wrong here. Yeah. Oh, checking the wrong one here. Yes. I guess we don't need this then. I don't think. Okay, we got it in the format that we like, right? In a dictionary. Okay, now we can do, well, we can run a DFS function here, right? So we can do, well, def DFS. We pass in our graph. Find all possible paths from node 0 to node n-1 and return them in any order. Okay. We need to go from node 0, right? So we go from node 0. Ooh, just ripped ass. Ooh. Okay, graph 0. Let's go 0 and, oh shit, no, this would be node. And then this would be destination, right? ADJ list here, we want to pass in all DFS, pass in our graph. Our node is 0 and our destination would be, well, the length of the array. So let's do destination is equal to the length of graph, right? And let's print that just in case, because I don't know. Oops, sorry, we want to print our destination. We got 4, 0, 1, 2, 3, right? But we want length of n-1. We should be 3. Yes. Okay. So we got that. Now we can put back here. And then we can do, well, DFS graph node destination, right? I guess we probably need to pass in some sort of res array, right? Like, because we need to return it as a res array. Res is equal to this. We need to do all the different destinations. I mean, there's so many different destinations, right? Like, I'm going to keep this res array for now. I'm not going to put it in. We got to think, well, what's our base case? Well, if is it guaranteed that we're always going to find something? Input graph is guaranteed to be a DAG. Okay, all right. So we don't have to do anything else. So we can just do, well, if any other base cases, we can just do, well, if graph is equal to destination. We're going to need to make some sort of like, I think current array. Right? I mean, it's definitely a tough recursive function here, right? Because really when we get to our max, right, we want to append to res, right? Res.append. We want to append like a copy occur, right? So that means I think we're gonna pass in res up here. Okay. Sorry, if node is equal to destination. Okay. I think when we start our thing, we have to make a local copy of cur, right? Well, no. Would we make a local copy of cur? I don't know. Maybe not. Because we're going to keep resetting cur every time we do this, right? So how can we... How can we remember our input through the recursive functions? How can we remember our input, right? Technically, we got to go through the functions and like kind of like return that node and append that node each time, I'm thinking. Okay. I'm not sure how we can do this, right? Maybe we can ditch this cur. Alright, let's think about this. We know that that's our destination, right? Then we want to loop through, right, for neighbor in graph node, right? We know that we don't have a cycle, so we don't have to check if it's in the set, right? I don't think we have to check if it's in the set. I mean, we don't need a cycle, so it's an acyclic graph, so we can call our DFS function here. We pass in our graph, our neighbor, our destination, and our res, right? Maybe we can declare our cur here, right? Because technically we're entering the for loop here, right? We enter the for loop, we declare our cur, we call this function, right? And it keeps calling, right? We return it and add it to our cur, right? So we make this like some sort of variable, like I guess like cur path is equal to, we do node plus DFS neighbor. Something like that, right? And then once we get outside of here, we do well cur.append and we append it to res. So we do something like res.append, we append cur.copy, right? Can we just like return our res? Do we have to return anything? I'm not sure. Let's just leave it at that for now. We have our res here defined. We can just return our res, right? Let's see what we get. Probably won't run. There's probably something wrong. Node is not defined. Did you mean mode? Oh. Oh shit, we want to return a node here, right? So we just want to return node. We can't add here. Do we have to flip this into like some sort of bracket or something? I don't know. You're redefining graph as adjacent list, but still using the original graph later. Oh my god, dude. Jesus. Adjacency list. Alright, because then this doesn't matter. You're returning just an integer node when you need to build a path or list of nodes. The return isn't useful for path construction. Cur path is invalid. Okay, so destination, we have our res. We pass in our adjacency list. We pass in our node. We pass in our destination. And then we pass in our, I guess this is our current path. I assume, right? Yeah, our path. Path, right? If node is equal to destination, we want to append our path. Res.append path. Copy of entire path, right? So we get that. We have the same here. And then we loop through our neighbors, right? Can get rid of this cur because we're not exactly using this anymore. And we just call our DFS function. But instead, we add our path plus our neighbor. Then we can get rid of this too. There we go. Okay. We were close. Like, good thinking, but it's not quite there yet, you know? Yeah, that's good. Anyway, let's jump into a BFS solution, right? So let's get rid of this. Let's actually just highlight DFS here. It's so funny that we go up, like, it's so stupid. Anyway, okay, let's get rid of this, right? So now we can kind of think about, okay, how can we do BFS for this now, right? Do BFS, pass in our list, have our current node, our destination, our current path.
Who's your favorite UFC fighter? I mean, I've always been a fan of Ronda. I actually.
Okay. So now we want to define our BFS, right? Pass in our adjacency list. We have a 0. We have our destination, our current path, and our res, right? We want to import our queue here. So from collections, we want to import a DQ, right? Loop through here. This is actually our path, right? This is our node. Whoops. Okay, we want to do, okay, well, we want to append our first value into our queue, right? So we would do, well, we want to initialize our queue. Queue is equal to DQ, right? Again, I think with this, we need to make it local. I think. Pass in our node and our current path, right? I think. Okay. And we do while queue, right? We pop from our queue. Queue. Sorry, we'll do node and path is equal to queue dot pop left, right? We loop through our while loop, then we need to check, well, if node is equal to the destination, right? Then we want to do, well, res.append path and include all of it, right? Just slice, but includes everything. Other than that, we want to loop through, well, for neighbor in node I, we want to check, A neighbor in adjacency list node. We want to do, well, q.append. We want to append our current neighbor. Alright, so how would we do this? We'd append our, like, I think maybe we just append neighbor, and we'd append our path plus our neighbor, I think. I don't know if that's the way you want to do it. I believe that we're probably going to have some error here. Oh, no. It just accepted right away. There we go. That is our BFS solution. Nice. Add a little BFS here. BFS. Okay. That's a good problem. Let's take a look at another problem. Let's do the difficulty, do it by acceptance. Find the city with the smallest number of neighbors at a threshold distance. Find champion 2. Have we done find champion 1? I don't know. Count the number of complete components. I think that would be a good one. Let's take a look at this one. A classic problem. You're given an integer n, there's an undirected graph with n vertices numbered from 0 to n minus 1. You're given a 2D array edges where edges I is equal to a, y, b, y. Okay. Again, we're given 0, 1, 0, 2. 1, 2, 3, 4. Okay. Okay. A connecting component is a subgraph of a graph in which there exists a path between any two vertices and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. A connected component is said to be complete if there exists an edge between every pair of its vertices. Okay. I definitely think okay. If I was given this in an interview, I think really what we're looking for here is we're looking for a cycle, right? If we find a cycle, then we know that this has to be a completed component, right? But really, every time we start a BFS, right, we want to increment our count, right? Because that node isn't seen, we'd want to increment our count, right? Now, I think you can do this with both BFS and DFS. I don't think it really matters. Yeah, you can. You can do union find too. Fine, yeah, using BFS here, you're just going to count the number of nodes. Yeah, that's what I said. Or count the number of nodes and edges in the component. A connected component is complete if and only if the number of edges in the component is equal to m, where m is the number of nodes in the component. Okay. Whatever that means. I don't know. So I'm thinking here, what we want to do to solve this problem is let's convert it to an adjacency matrix first. Because again, I like to work with adjacency matrices, especially as a Okay, let's do, all right. Oh, so we have to initialize our graph, right? And we do, well, for edge, in edges, right? We do AB is equal to the edge, right? So, currently looking at this one, AB, 0, 1, 0, 2. Alright, but we have to do it back too, right? Because 1, 0 would be 0, 1. Right, because it is an undirected graph, right? So we have to do both the edges. So we have to check, well, if A, not in graph, then graph A is equal to this, a new list, right? Okay, then graph B is equal to a new list, right? Oh, sorry, whoops. We do, well, if B not in graph B is equal to this, then we do, well, graph A dot append B, graph B dot append A, right? We simply will just, outside of our 4 here, oh, we've got everything outside of our 4, which is not good. We want to return our graph. Right, now we just need to call it. Let's make our graph equal to the adjacency list here. We pass in our edges, right? And then we just, let's print our graph. I believe that should be good. Okay, right, so we've got our adjacency list here. 4, 3. 0, 1, 2, 3, 4. We're missing one right now. N is equal to 6. How can we add this extra one? We have an issue here. 2, 3, 4, 5. Right, we're missing a simple graph here. Right, we just passed in our edges. How can we do this differently? Well, let's do, okay, well, for I in length edges, are we given an N? Oh, okay, we're given an N. For I in length N, let's do graph I is equal to this. There's no length N. For graph in, we need range here. Okay, there we go. One, 0, 2, 2, 0, 1, 3, 4, 5, 4, 3, and then 5, 3. Okay, I believe that worked. But then I don't think we need this here. I believe that is a redundant operation right there. Okay. All right, so I think that looks good now. Okay. let's think about this now. So, obviously we're gonna need a set, right? We're gonna need once this graph are complete, right? So, I think the best way to go about this is probably a BFS approach. So, what are we returning here, right? We're returning an output, our number of edges, right? So, let's call our BFS. We pass in our graph. We pass in our starting node, right, which is 0. And we pass in our count, right? Count equal to 0. And we just simply just return our count, okay? At this point, we have to import a queue here from collections, import a DQ, right? We do, well, I'll do def BFS. We want to pass in our graph, pass in our starting node, pass in our, like, let's call it total count, right? First of all, we want to create our graph, right? So let's create our we want to create our queue, right? So we would do, well, queue.append. No, sorry. Q dot what? I'm freaking blanking out here, dude. Yeah, we'd append to our queue, right? So we want to append our current node. Do we need to append our total count? I don't really think we do, because we're not counting anything. I believe we need to, because we're not keeping track of like a depth or something that we'd require to pass in our count. So I only think we really need to pass in our node, really. So we do while queue, right? We'd pass in, we'd pop, right? So we'd do, well, okay, our node is equal to q.popleft, right? Okay, we want to check, well, if we find a node that we have already visited, right? So let's say every time we jump back into the queue, no, that wouldn't work, right? We'd finish our queue. Okay, let's think about that later, actually. Okay, let's do well for neighbor in graph node, right? We need to create a visited set, right? So our visited would be inside of our while, right? Because inside of our while, we're looking at the current component, right? So we need to have it inside our while, okay? Create a new visited set, and we check, well, if neighbor not in visited, right? Then we can finally append our queue, right? And then we'd append q.append, we'd append our neighbor, right? So we keep going through. Once we get through our while, we get out through outside of our for. Maybe we can increment our total count from outside. So we'd append our BFS here. We have visited, right? Keeping track of what's currently looking, right? Once we finish this while, we're basically done with that node, right? We go back out here, right? We're probably going to need some sort of for loop that's looping through each thing, I think. So we do well for let's call it I. Oh, we can call it node, I guess, right? Yeah, we can. For node in graph, right? We're calling the BFS function on our current node, right? Maybe we can make a global set, right? Because if we make a global set here, I mean, really, we're not going to be visiting these nodes again, right? Because we make a global set, we're going to start here, go here, go here, find that we've, have a thingo here, boot out of it, right? Then we're going to come back in with that global set again. We're going to see we've already visited that value, and it's not gonna return anything, right? So I think that's the way we should go about it, right? Go well for node and graph, right? We call our BFS, okay? And I guess this can return our count, right? And here we can update our max count. We can call this our max count. We can call this our count instead, right? Loop through. Our max count is equal to max. We can do, max count plus or equal to count, right? Okay, so we're incrementing our count each time, right? So in here, if we get to the end of our while here, and we see, well, okay, we've got through here. We got through our for. Ow. Okay. We append our node. We enter our queue. I think we gotta get rid of this visited, right? We actually gotta pass in a visited, and we gotta create one. Visited is equal to set, right? We pass in our visited. Okay. So now visited is now passed in to our BFS function. So we have a global visited function now. Okay. That's keeping track. I believe this is keeping track. Neighbor not in visited, q.append neighbor. And this is where we append our visited. Visitor.add neighbor, right? We would check down here, right? Well, if node not in visited, then we'd want to append this. We do this here, right? We'd append our count over here. Count plus or equal to 1 as soon as we enter it, right? Because we're checking here that if it's not in visited, because if we get inside this while loop, then we can count this as a component, right? Then down here, once we get through, we can return our count, right? So then in increments here, right? We get our well count is equal to BFS, right? And then we increment our count, right? And we return our max count. Now, there's definitely something wrong here. I don't think probably my logic probably works out. There's definitely probably something wrong. But let's take a look. Cannot access local variable count. Okay. Where it's not associated with a value. I didn't think about this. Okay, so we pass in our max count here, right? I guess when we pass in our count, right, we can just pass in 0 really, right? Because I think there's definitely a better way to do this, but we can pass in 0, right? Q is not defined. Oh shit. Q is equal to DQ node. Why is this not working? If our max count plus or equal to our count. Let's print every single node that's coming through here. Print every single node that 0, 0, we get 3, we get 5. Okay, over here we get 0, expected 1, output 2. Why do we expect 1 here? The component, since there is an edge between every pair of 2 vertices. On the other hand, the component containing vertices 3, 4, 5 is not complete since there is no edge between vertices 4 and 5. Okay, so we're looking for complete graphs. Okay, that changes it a little bit. Well, at least I think the way I kind of thought about this, if it's like we're just checking for 2 separate components, I would have got the right answer, I think, because... So I'm kind of happy about that. That's 1. But now we have to edit this to make it detect cycles, right? So, man. Okay, we can keep this. I think this is good. But when we do this queue here... I think what we need to edit is, well, instead of appending our count here automatically at the front, right, we need to detect when we have seen a neighbor, when we have actually seen something and visited, right? So if we've seen something and visited, we know that it's a cycle, right? So I guess we can add an else statement here and just add count plus or equal to 1, right? Because if we see something technically, right, if neighbor not in visited, right, so if our neighbor is in visited, then we just add 1, because then we know that it's a cycle, right? So we can automatically just add 1, right? Else, I guess we just like append 0, right? If that 0 is automatically in here, so count's always 0, we return our count and it's 0. And every time we add here, or adding 0 to something is just always 0. So, okay. Nope. We get an output of 8 now. Okay. It's because we're automatically always counting, right? Well, I think we're going to see multiple different ones here, right? So we start at 0. Then we're going to do, well, for neighbor and graph node, we're going to append 1 and 2, right? So we see 1, see 2. Right? I think that's how we get 6. I think we'll keep adding it, right? So I think what we got to do here is we just like simply, if we return something, maybe we just simply got to return count. We just got to return count plus 1 as soon as we see something, right? Ooh, expected 1, but we got 2. Looking at nodes both 0 and 3, but how? Oh, I see why. I think it's thinking this is a... Yeah. We've got this because it's an undirected graph, so we're going back and forth, right? So I think what we got to do is we got to change our adjacency list, right? We got to change the way that we're thinking about this with in degrees and out degrees. As everything's technically a cycle, right? I feel like in an undirected graph, everything is technically a cycle, isn't it? In an undirected graph, it's technically everything a cycle. No, in an undirected graph, not everything is technically a cycle. A cycle is a closed path in a graph, meaning it starts and ends at the same vertex, while a simple path doesn't repeat in any vertex. Okay, that's what I'm thinking here, right? Because I have my adjacency list, right? You know, and technically I have a path from 3 to 4, but then back from 4 to 3, which technically would then, I think, trigger this here. The reason why we only get an increment by 1 is because we're just automatically returning everything, right? Because of that. But how can we do this? I'm not sure how we could detect this, right? Yeah, I really don't know. In degree and out degree of each node is... I'm gonna have to add something that can detect this, right? So if we move from 3 to 4, yeah, man, I'm not sure, dude. Yeah, bro, I really don't know. Number of complete components. Yeah, I'm not sure. I'm gonna have to ask GPT for some hints, bro. I really don't know. K should have exactly K times K minus 1 over 2 edges to be complete. You're not collecting the number of edges in each component which is needed to validate the completeness. Okay. Okay, so we have to count the edges. That's what they give me, bro. While Q. If we can keep this, right, we build the adjacency list, right? Simple. Okay, we have graphs with that, we have visited set, and we have a max count, right? We loop through the nodes in the graph. for node in graph. If node not visited, we have that. And we have node and edge count is equal to BFS node graph visited. If K is equal to length nodes, you minus 1 over 2, and then complete nodes plus equal to 1. Okay. So let's do, okay, well, what do we want to get from this? We want to get, well, nodes, the edge count. Okay. Then we do K is equal to the length of nodes if edge count is equal to, so this is how we would find this, K times K minus 1 over 2, right? We would increment our max count plus or equal to 1, right? We just want to return our max count, right? Now we go into our BFS function, right? They pass in a start, they pass in a graph, and they pass in a visited set, right? We pass in our start, we pass in a graph, we can get rid of the count, right? Count is not needed in here. Which means we can remove that from here, right? We don't need the 0. Okay. Simple. We enter our queue. We check our node, we pop left, we do for neighbor in node, right? Okay, we increment our edge count by 1 for each neighbor, right? Edge count plus equal to 1, right? So they have the DQ here, they do visited dot add node. I guess we can call this start, so we don't make any start, right? Then we do, okay, nodes is equal to start. So we're making an array of nodes, right, that we're visiting. We create our edge count here, right? Move through, we increase our edge count, we check our neighbors. We then append our neighbor. We do visited.add neighbor, right? And then we do, okay, we append to our nodes. Nodes.append neighbor, right? We can get rid of this else. And simply we just return our nodes and our edge count divided by 2. Since each edge is connected twice. Okay. Alright. Counter access to local variable node. Sorry, man. Your start now. I'll get you confused. Here we go. So we were close. You know, we thought about the problem properly. I feel like we executed it properly using BFS. But, you know, in the end, you know, we just messed up. You know, we didn't read the question properly, pretty much. About to get a freeze warning, dude. What is going on here? Freeze warning. Oh. See, what is the weather gonna be, bro? Freeze warning in effect from midnight tonight to 9 a.m. Tuesday. Freeze effect. Temperatures as low as 25. Dude, no way. Bro. So tomorrow's gonna be cold. Well, not too bad. Wednesday, Thursday, raining. Ooh, the weekend's gonna be nice, man. That's good. Okay. Alright. Nice. Okay. Yeah, no problem. Do we want to do the DFS solution? I think we should. What do we got time left here? We've been going for about an hour. Sorry guys, I gotta fix my mic. Okay. All right. Yeah, I think we're going to do the DFS solution. We're going for about an hour, so I think we'll do the DFS solution. Then we're going to jump into something else. So I think it's important to think about the DFS solution as well. So, let's do that, right? Let's get rid of this crap. Actually, let's submit it. Call this the BFS, right? Submit. All right. Wow, 3,356 test cases, bro. Jeez. I think we can keep this part here. Really what we just gotta remove is that BFS here, right? So obviously we want to create a DFS function now. We want to pass in our, I guess, our graph, our start, and our visited, right? Now let's think about this, right? We're not using a stack. We're actually using a recursive function, so we have to think about this differently now, right? So we have our for node and graph. We have our for node not in visited. We print the node. I think we have to think about the same thing, right? So I guess we can think about it in the same way, right? Okay, so that's right. First thing here is we probably want to add I'm thinking here now, I think we probably want to add in visited not as a global array because I guess we can get a new visited array every time we loop through this for. So I think that should make it work. Every time we loop through this for, it resets the array. So each time we get to a new node, it resets the array. So I think that should be fine now. So pretty much we jump in here and we check, well, we want to do our base case. So if start is equal to visited, right? And we pretty much just want to return our nodes and our edge count, right? Okay, so but I think now we're gonna have to pass in the actual like nodes is equal to node, right? And then edge count is equal to 0, right? I think we're actually gonna have to pass this in now. Pass in our nodes and we pass in our edge count because, you know, I don't think we can keep resetting this inside the recursive function, right? So we do, well, if start is equal to visitor, return nodes, edge count, then we loop through, okay, for neighbor in graph start, right? We want to check, well, if neighbor not in visited, right? Then we can add it, right? So we can do, well, visited.add, pass in our neighbor, okay? We can do, well, nodes.add, nodes.append, pass in our nodes and our, what's the other one? Our edge count, right? We append our nodes.append. I'm thinking about the way we want to call this function. Do we want to add our visitor first, then call the function, then append the nodes, and then append that? Because then maybe we could be appending like multiple times. Well, we need to increase our edge count by 1, right? Plus equal to 1. Edge count plus equal to 1. I think we have to call our function here, right? DFS graph neighbor visited nodes edge count, right? I think in the beginning we got to add our visited, so visited.add. This doesn't really matter obviously because visited doesn't hold any duplicates, right? So we can, you know, keep adding the same one, doesn't really matter, right? Visited.add. We add our start. We check. Right? We loop through this. We add the visited, right? And then we call the function, right? Because visited is really the only one that really matters here, right? Call the function. We do it again. We add visited, right? Once we reach this, right? Oh shit. Once we reach this, we're going to instantly return nodes and edge count. We're going to instantly return nodes and edge count to the next function, right? Which means we're going to start at 0. We're going to append the node, add the edge count. Append the node, add the edge count. I'm thinking, well, do we need another return statement outside of here? Right? Do we need another return out here that returns outside of this for that returns the nodes, the edge count over 2? Right, because we're going to keep looping right until we see it. We're going to return this. It's going to be 0, right, because we're not returning anything. Then we return from here, we add, we return to our next function, and then we add, we return, we add, and then we finally return, right? So I think that's probably the way to go about it. Edge count is not defined. Whoops, this is meant to be edge count like this. We got a 1. All right, this is not printing now. Okay, well, we are printing the right ones. We're going from 0 to 3, 0 to 5. Here we're getting an output of 1. We're expecting 3. Getting output of 0, expecting 1. I'm not sure, honestly. You're very close to a working DFS. Start is equal to visitor is incorrect. You're comparing an int start to a set, which will always be false. Oh my god. What are we comparing, dude? You're appending the whole list of nodes into itself. So you should be appending the neighbor you're visiting. Oh my gosh. Neighbor. Comparing it to a visited set, right? So we'll have to compare, well, so then what's the fucking base case here, dude? We don't have a base case. Okay, so this needs to go, apparently. We have our nodes is equal to this, right? DFS. Get rid of edge count. We increase by 1, we return the max count. Okay, so now we need to look inside our DFS function, right? So we have, get rid of this. Visitor.add. Visitor.add start. Nodes.append. We append the current node, right? This is the node, it should be start. Edge count is equal to the length of graph node. Count all the edges from this node. Okay. Remove this. Apparently it's not needed. For neighbor in graph start, if neighbor not in visited, then we can just increase the edge count. Edge count plus or equal to DFS neighbor. Sorry, DFS graph neighbor visited nodes. And we just return our edge count, apparently. This has to be DFS. Interesting problem. Like, why does DFS not have enemies key? Is your implicit base case? My God, no way. Okay, that's enough graph problems for today. Let's look at one more problem today because we've been going for a little while. I need to get ready to do some stuff, so let's take a look at like a greedy problem or something. Believe we can get that from our list, right? Our powerful study program. Take a look at a greedy problem. Water bottles. That's a good one. Nice little easy problem. There are num bottles where water bottles are initially full of water. You can exchange empty water bottles from the market with one full water bottle. The operation of drinking a full water bottle turns into an empty bottle. Given the two integers num bottles and num exchange, return the maximum number of water bottles you can drink. Num bottles, water bottles are initially full of water. You can exchange empty water bottles from the market with one full water bottle. I'm so confused right now. Initial. I'm a little confused about this problem. Seems like a fairly simple problem, but I am a little confused by the water bottles. Help me understand the problem. Don't show code. Goal is to figure out how to maximize the total amount of water you can drink, often with specific rules and constraints. Okay, yeah, I understand this shit. You're given two main pieces of input: the number of water bottles, the amount of water each bottle initially contains. There could be some specific rules to how you consume or transfer the water, such as the goal. The objective is to maximize the total amount of water you drink, or the number of times you can consume water from the bottles, possibly under certain rules like limiting how many times you can transfer a drink from the single bottle. That doesn't really help me at all. You can exchange 3 empty bottles to get 1 full water bottle. Number of water bottles you can drink: 9 plus 3 plus 1 is 13. We start with initial of 9. Okay. I don't really get this, dude. Anyone here from the contest? Yeah, I don't really understand this question either. No, I don't want to see the solution, bro. Oh my god, dude. Where are these people, dude? I just want to understand this problem. I don't get it, dude. There are num bottles, water bottles that are initially full of water. You can exchange, exchange empty water bottles from the market with one full water bottle. Okay. So I can exchange 3 empty water bottles from the market with one full water bottle. The operation of drinking a full water bottle turns into an empty bottle. Okay. Given the 2 inches num bottles and num exchange, return the maximum number of water bottles you can drink. Okay. So I think we can drink. Okay, I understand now. We can drink 9 here. It goes to empty, right? We can pass the 3 empties, right? Because 3 empties get us an extra bottle. So then we can drink those. Then we have 3 empties. Have 1 more. Send it off. Okay. Alright. I understand now. Okay. Interesting problem. So obviously I feel like I guess we can call this like total water bottles drank, right? Total bottles drank, okay, is equal to 0. Okay, so we have total bottles drank is 0. Okay, then we can do, well, total bottles. Okay, let's do num bottles and bottles is equal to num bottles. Okay, while n bottles does not equal 0, right? We want to do this loop while the bottles does not equal 0. Okay. The num exchange is 3, right? So we need while our, I guess while our n bottles is less than, while num bottles not less than how the hell do I do this in a while? It's not less than num exchange. How do I do this in Python? Like, do while n bottles is not less than num exchange. Okay, yeah, okay. I don't know why I didn't think about this. I'm so stupid. Okay. Well, is this greater than this, right? Then we can do, well, let's do, okay, let's do like bottles drank is equal to 0, right? So let's do, okay, well, m bottles is equal to, sorry, bottles drank plus or equal to m bottles, right? Then we can do, well, okay, we have 9 bottles drank. Okay, let's call this res. This is really confusing to do this, dude. Oh my god. Alright, bottles drank is plus or equal to m bottles. Okay. So then we can add this to our res. So let's do res plus or equal to bottles drank. Okay. Okay, then we need to do, well, we need to do bottles drank modulus num exchange, right? Bottles drank new bottles is equal to modulus num exchange here. Oh shit, dude. Man, this is tough to think about in my head, right? This is only going to give us the remainder, right? I'm not sure how to think about this, how to think about 15, 18 water bottles. Add bottles drank to res. Alright. We need to do, well, new bottles. And bottles. Well, then we need to do, okay, we need to do, okay, bottles drank divide by num exchange. Do n bottles is equal to bottles drank divided by num exchange, right? Then we go back. But we might have some extra bottles, right? So we would return our res. This is wrong. I know. I just want to see. Okay, it's not going to print because we have a while loop here. Okay. We need some sort of modulus operation to get the remainder, right? Because it's not always going to be dividing, right? Two bottles drank is equal to bottles drank modulus num exchange, right? I'm running out of time here, bro. I gotta do some stuff, so you're on the right track. I am on the right track. M bottles equal to num bottles. Bottles drank is equal to 0. Okay, while n bottles is less than or equal to num exchange, bottles drank plus or equal to n bottles. Here we need n bottles is equal to n bottles divided by num exchange plus n bottles. They do it on one line, the modulus num exchange. Okay, after the loop. Bottles drank plus equal to n bottles, right? This drink's remaining bottles that can't be exchanged. And then we return bottles drank. Get rid of this res. We were close. We had the right way of thinking. Ooh. What is wrong here? Probably have a typo, but n bottles divided by num exchange plus n bottles modulus num exchange. Okay. This shit is stupid. Let's take a look at some of the solutions. Because I gotta go, man. Total bottles is equal to non-bottles. N bottles equal to non-bottles, right? So we can get rid of bottles drank. Well, n bottles is greater than or equal to num exchange, then we can do n bottles plus or equal to num bottles over to num exchange. Num bottles is equal to num bottles over num exchange plus n bottles over num exchange return total n bottles. Probably got infinite loop now, dude. Oh my god. I'm gonna switch this to total bottles to make it more clear. Total bottles, num bottles, total bottles. What's equal to num bottle? I'm not gonna submit this just because I didn't really do it. I want to come back to it. Okay. We'll come back to this one. But yeah, I appreciate you guys watching. I will see you tomorrow.